spirit. Spaglioni con i polini, vero?
Okay. I don't know if you can start. 1 minute.
Okay.
So here you can.
Can I use this one?
Yes. Okay. Okay. Oops. So the someone will share.
Probably.
We'll
Yes,
share we share the presentation. Okay.
Everybody have to share the presentation.
So okay, the first one can share and start.
Okay, let me introduce.
Okay, you can
Hi,
open.
I'm Giulio Biondi.
Sorry?
I am the technical assistant in this discussion. My name is Giulio Biondi.
Okay. Thank you. So just 1 second. Hi everybody. Can you hear me?
Yes.
Yes.
Okay, now we are online. Okay, thank you very much. Let me introduce myself. I'm Alberico Sonnessa from Polytechnic University of Bari, and I'm the chair of this session that is Geomatics for Resource Monitoring and Management. This is the second part of this session, and we can move quickly to the first presentation that should be hosted by Noemi Pagano from Polytechnic University of Bari. And I hope Noemi is online. Noemi, can you hear me? No. Probably we have got some problems with the connection, I don't know. So I need help from the technical assistant.
Yes.
Okay. Probably nobody can hear me there.
I can hear you.
Okay, you can hear me, but I don't.
I can see
Okay.
Noemi Pagano is connected.
Okay. Did you hear my introduction?
Yeah?
Yeah. Okay. So you heard everything, and I
Yes.
don't know, but I don't have no feedback from people at home, from people
Yeah.
online.
For me, it's
Yes.
okay.
Yeah,
It's okay.
everything was working and we could hear you properly.
Okay. Okay. So let me call again Noemi. Noemi, are you online? Probably not. So we can move to in the meantime, we can move to the second presentation. Just let me check the list. Yes, the second presentation should be hosted by Federica Mesto from Polytechnic University of Bari. Federica, can you hear me?
Yes, I can hear you. Good afternoon.
Oh, good, good. Thank you.
I will
Okay, if
share
you
my
want,
screen. Yes.
yes, please.
Okay. Can you see the presentation?
Yes, perfectly.
Yes.
Okay. Good afternoon. My name is Federica Mesto, and I am from the University of Bari. Today I will show you our work entitled Integrating Multi-Source Geospatial Datasets in Distributed Hydrological Modeling, a case study of the Podoniftis Basin in Athens. So the motivation behind our work is that traditional models usually rely on lumped parameters and basin average characteristics. And even if these are quite computationally efficient, they can lead to simplified representation of runoff. While in urban catchments, so in cities, we have that topography, land use, and soil properties can vary very quickly along short distances. And so this is the reason why distributed modeling is useful in these cases, so to simulate the behavior of urban catchments, because parameters vary along the domain, and so we can have an improved representation of runoff and a better flood hazard assessment. Moreover, distributed modeling allow the use of high-resolution geospatial datasets. So I would like to show you the distributed hydrological model that we used. It's called DREAM model, and it stands for Distributed Model for Runoff, Evapotranspiration, and Antecedent Soil Moisture Simulation. It is a process-based and spatially distributed hydrological model, and it is grid-based. So the entire domain is divided into cells, and for each cell, the model can solve the soil-water balance. And it can simulate precipitation, interception, evapotranspiration, surface runoff, subsurface exchange, and groundwater recharge. So the DREAM includes two submodels, so it can work on a daily scale, but also on a hourly scale because it can simulate events with an hourly time step. Moving on to the case study, we studied the Podoniftis Basin, which is located in the Attica region, very close to Athens in Greece. And the main characteristics are an area of 77.6 square kilometers, and it's a highly urbanized catchment. So the impervious surfaces cover more than the 50% of the basin. So the main challenge here is to represent with the hydrological model the behavior of this urban catchment because it can show a rapid hydrological response due to urbanization. It is important to give a regulatory framework, and at the European level, we have the Flood Directive, which requires for flood hazard and flood risk assessment. And at a national level, so in Greece, we have the flood risk management plans that require the use of design rainfall scenarios for flood hazard mapping. Usually, the classical workflow for flood hazard assessment requires the synthetic hydrograph, sorry. So it's the precipitation with a return period, for example, for 100 years. And this is the input of the hydrological model. And the output of the hydrological model is the discharging time, so the hydrograph, which is computed at the outlet section of the basin. Usually, the hydrograph is used as a boundary condition into a two-dimensional hydraulic model so that we can compute potentially floodable areas. So we used multi-source geospatial information. For example, we used the digital elevation model with a resolution of 2 meters for the topography and the Korean land cover for land use and the Lucas topsoil dataset for the sand and clay and organic matter percentage. So as we can see, the resolution of these inputs of these datasets are quite different from each other. They not only have different spatial resolution, but also different formats because we had TIFF files or shape files. And so different datasets and they have different characteristics. So they require a GIS harmonization, for example, reprojection, clipping, and resampling, to have an harmonized input for the distributed hydrological model. So concerning the data harmonization workflow, we started from the raw datasets, as I mentioned previously, and these datasets require the reprojection into the Greek coordinate system, a clipping to the basin boundary, and the rasterization or interpolation, resampling, and all these processes are useful to obtain a 10-meter computational grid, because the domain in all the basin is divided into cells with a 10-meter resolution, and all the output of this workflow is in ASCII format so that the model can read these files and do the simulation. Of course, the GIS processing is the foundation of distributed hydrological modeling. So we started from the DM-based terrain analysis, and we used a digital elevation model from the Hellenic Cadastre, so from the LSO25 project, which is derived from a large-scale aerial photogrammetry, and it is nationwide. So we have orthophotos all over Greece. And the processing steps here are the bilinear resampling, because we had to go from 2 meters resolution to the 10 meters resolution for the computational grid. And of course, the sink filling, because we need to remove depressions in order to make the computation for the terrain descriptors. And for terrain descriptors, we use slope, flow direction, and flow accumulation. And these are all maps in ASCII format that we use into the hydrological model. And this is very important because topography controls runoff generation and flow routing. So for land use parameterization, we used Korean land cover classes in a shapefile format and a resolution of 100 meter. And we needed a reclassification from literature to reduce the number of categories to 17 categories, and also to do the assignment of 2 important parameters, which are the Manning's roughness coefficient and the root depth. And with this procedure, we could also aggregate these classes into 5 classes, which are required by the DREAM model. As we can see on the picture, most of the basin is impervious area, so it's highly urbanized, as I said previously. For the soil data processing, we use the soil information from the Lucas topsoil database. It has a resolution of 500 meters. We had these input variables. These are TIFF files, especially the sand content, the clay content, and the organic carbon content in percentage. And from these 3 maps that are available across Europe, it is possible also to have the texture USDA. So we have 12 classes of soil type. The processing required the nearest neighbor interpolation for soil classes and bilinear interpolation for continuous variables, such as sand, clay, and organic carbon content. So here also the maps of sand, clay, and organic carbon are the output in ASCII format, and they are useful for the use of pedotransfer functions that are into the model and that lead to the derivation of the hydraulic properties of the soil. And these are, for example, the volumetric soil water content at saturation, or volumetric soil water content at field capacity, or also the permeability at saturation. And these quantities and these parameters are important to have an information about the soil water content for each time step, because it is equal to the volumetric soil water content at the time step multiplied for the root depth. So once all the input data were harmonized, we used the design rainfall event with a return period of 100 years. And this is the hydrological forcing. So for each cell of the domain, we have the input, we have the precipitation, and so the model can simulate all the processes in each grid cell. For example, it simulates interception, surface depression storage, infiltration, percolation, real evapotranspiration, and subsurface flow and surface runoff. And these quantities must be propagated, so the runoff computed for each cell must be propagated along the basin. And this is done according to the travel time, so the flow time of each cell. So the model can compute the discharge in time and give as an output the hydrograph in the outlet section of the basin. So as we can see on the left, the hydrograph shows a rapid rise of flow and a short lag time, which is typical of an urban catchment. And we can see the strong influence of the impervious surfaces. So the basin reacts very quickly to extreme rainfall. And also the model outputs are some maps that represent the runoff volumes. For example, on the right, we have the runoff volume at the 7th hour of simulation, so corresponding to the peak of the hydrograph. And these time-varying runoff maps show that we have a higher runoff along the drainage network, but also in urbanized sector, while in semi-natural areas, we have lower runoff. And unlike lumped approach, the distributed modeling provides especially explicit runoff information across all the catchment. So what are the challenges of distributed modeling? Of course, in this approach, we had to go from 2-meter resolution to 10-meter resolution of the digital elevation model. And of course, this can be used in subsequent analysis. For example, in hydraulic simulations, we can use a 2 meters resolution. But for this study, 10 meters in an urban area are quite detailed. Also, the Corinne land cover doesn't see small urban features. And of course, in the future, we can include high-resolution urban land cover, including green roofs or urban gardens or small green areas. And also for the soil properties, we have these generalized soil properties, but with the local surveys, we can have a better information about it. And concerning the modeling, we have that rainfall doesn't have a spatial variability, so it varies during time, but not in space. And also, we have a limit in the DREAM model that we have a simplified routing. So, for example, we don't look at the sewer network, but since we are modeling an event with a high return period of 100 years, the sewer network doesn't have a big influence on the results. And also, unfortunately, we don't have observed data of discharge, so the calibration could not be properly done like in traditional studies. But all these issues can be solved also in the subsequent analysis. So coupling the hydrological model with the hydraulic model to have hydrodynamic models that can account for urban drainage also. So concluding, we can say that multi-source geospatial datasets can be successfully integrated within a GIS framework, and the GIS preprocessing is essential for consistent model parameterization. Also, distributed modeling can capture spatial runoff variability, and the gridded runoff outputs of the hydrological model can support future two-dimensional hydraulic simulation and urban flood hazard assessment. So this work highlights the importance of GIS-based preprocessing for integrating heterogeneous geospatial datasets into distributed hydrological modeling. Thank you very much for your attention. I can't hear anything.
Can you hear me now?
Yes, I can hear you.
Okay. So, just a curiosity, can you go better in detail about which parameter were calibrated and how did you estimate the parameters?
Yes, I will share the screen again. So we have this important parameter here, which is the initial soil moisture condition. So in the hydrological model, we have three main parameters. We have a coefficient of redistribution for the lateral flow, so for the subsurface flow, and also the parameter for the groundwater recharge, but these two parameters are kept constant all over the simulation. But the one that we used, and first of all, we couldn't do a real calibration, unfortunately, because we didn't have observed discharge. So we couldn't do metrics as we usually do for a hydrology simulation, but we had previous studies that could give us some values of the discharge. And the only parameter that we adapted somehow was the initial soil moisture condition, which is very important for event-based simulations. And we are in a dry Mediterranean climate, so it was a parameter that was very, very close to the wilting point. So this is the main parameter that we estimated.
Okay, right. Now can you hear me? No, not so.
Yes. Please, when you're not talking, turn off the microphone because we can hear strong feedback from your room.
Sorry, we don't understand very well. Okay. Okay, let's check. Let's come back to the first presentation. Noemi, are you online and can you hear me?
I can hear you. I don't know if you hear me. I'm trying to also share my video, but
Yeah, we can hear you.
okay. I will
We
try
can
to
hear
share
you not so well.
at least.
Are you sharing your screen?
Now, yes. Tell me if you are able to see it. But I think that you are not able to see my video.
No, we can see your presentation, so it's okay. You should.
Okay, sorry. Some technological problems.
Perfect. It's perfectly visible now.
Okay, please, the floor is yours.
Okay, thank you. Thank you for the presentation. And today's presentation is a preliminary stage of the research that aims to answer to a question. How can we transform a sparse set of highly accurate satellite observation into a continuous and statistically reliable deformation model? We will try to address this challenge following this path. Before diving into the technological aspect of the methodology, it is important to understand why we are focused on this specific issue. Hydrological instability represents one of the major natural hazards in Italy. According on the latest ISPRA reports, approximately 95% of the Italian municipalities are exposed to landslide or flood hazard. The situation is particularly critical in the Apulia region, where more than 90% of municipalities are affected by hydrological or flood risk. Among the available technologies, multi-temporal INSAR has become one of the most effective territorial monitoring tool on a global scale. Its operating principle is based on analyzing the phase difference between the two images acquired by the same satellite at different epochs. Let us now focus on the study area. The research was carried out in the municipality of Chieti, located at the northern boundary of the Apulia region, close to the Molise region. The Chieti landslide has been documented for more than a century, and slow but persistent ground movement have progressively affected the urban area and producing a structural damage to the building and the public infrastructure. As shown in the figure developed by ISPRA, the landslide perimeters directly intersect a significant portion of the urban area. The zone classified as P3, so high level, and P4, so very high level of hazard, cover approximately 1.2 kilometer square. The first step consists of selecting a reliable satellite dataset and identifying the most stable measurement. The analysis was performed using the satellite Sentinel-1 dataset acquired in the descending orbit. This acquisition geometry was deliberately chosen and selected because it best matches the orientation of the investigated slope. The PS don't provide observation with the same quality. Some of them exhibit lower signal stability that is called coherence. So therefore, implementing precise coherence-based filter is essential. As we can see in the figure, the empty insert points are displayed. The color scale immediately highlights us the different deformation patterns that is affecting the Chieti municipality. Blue colors correspond to relatively stable areas, whereas red color identify colors and sector that are affected by highest negative deformation velocity, approximately minus 12 millimeters for each years. However, the same picture shows us one of the main limits of the empty insert technology. Measurements are not available when the PS doesn't exist, and also between them, no observation is available. So they don't provide us a continuous description of the deformation field. Before applying any interpolation technique, we first investigated the spatial organization of the available observation that we used, and it has been done with the Voronoi tessellation. The Voronoi diagram portions the study area into polygons and assigning each location in space to the nearest PS generator. Based on this, we computed the local entropy index, where the entropy is a quantitative measure of spatial disorder. Low entropy values indicate relative homogeneous deformation patterns, where neighbor observation exhibit similar behavior. Voronoi entropy provides a preliminary characterization spatial heterogeneity before the geostatistical model stage. The semi-variogram describes how the variability between the two observations change as the distance separating them increase. The underlying concept is, if two observations are close to each other and belong to the same physical process, we expect that have similar values. As the distance increases, their similarity progressively decreases. So this behavior is quantified and expressed by the equation shown in the slide. However, the experimental semi-variogram consists only to discrete estimated, and it's often affected by the measurement noise. So for this reason, it is necessary to fit a theoretical variogram model, and we tested three different variogram models comparing the stable, exponential, and the spherical models. Among the tested model, the spherical model provided the best representation of the observed deformation field with a coefficient of a deformation class close to 0.9 and the regression slope approaching. The validation phase has been done splitting the dataset into two datasets, but you can see how they were homogeneously and randomly distributed on the slope. So, by the calibrating parameters of the models, we executed the ordinary kriging algorithm to generate our continuous deformation surface. On the screen, you can evaluate the comparison between the interpolation performed. On the left side, you can see all the data, and on the right side, you can see the model generated using only the points that were with a coherence value higher than 0.5. The resulting map displays a move geological coherent velocity gradient, and thanks to this continuous model, we can now assess structural hazard even in the ambient urban sectors, gardens, where PS were not present, so they were absent. In conclusion, our study demonstrates that integration of Voronoi tessellation with advantage geostatistical allows to grow up the limitation of point-based satellite, and providing into a continuous tools for a territorial risk assessment. Looking forward, our main objective will focus on integrating other data providing by the Cosmos SkyMed satellite, and validating our models also using the high pressure precision leveling benchmark. Thank you so much for your attention and for your time. I hope that you heard me. I don't know. I can interrupt. I'm not able to, I hope that is not my problem.
Can you hear me, Noemi?
Okay, now yes.
Okay, that's my fault. Okay, there's just one question from the audience, I suppose.
Okay, thank you.
Okay, thank you, Nohemi, for your presentation. I just have a curiosity because when you were talking about the future development, you mentioned the integration of modeling and the labeling techniques. And so my question is, how do these two aspects combine?
Okay, thank you. Yes, as I told in the initial part, this is only a preliminary stage, and we want to validate our research also using the high level measurement that has been done in this country. How we can start using not only the sampling of the data set that we used, but verticalizing it using the angles of the satellite, and we can check at the first stage if the measurement of the leveling are close to our reconstruction, the geostatistical approach. I hope that it will work. We will discover in the future. Thank you for the question.
Okay, thank you.
Thank you very much, Noemi. And okay, we can move to the next presentation. The next work should be presented by Riccardo Tavolare from Polytechnic University of Bari. Riccardo, are you online? Yes?
Yes, I'm here.
Okay, please, the floor is yours.
Thank you. Okay. Good morning, everyone. Alberico, can you close your mic? Because there is some... Okay, thank you. Good morning, everyone. Today, I will introduce an automated pipeline for generating occlusion mask in photogrammetric workflow. The goal is to detect and remove temporary objects that are not part of the static scene, such as people, cars, trucks, so on, before the three-dimensional reconstruction process begins. This approach can improve the quality of the workflow under real-world survey conditions. The problem comes from one of the main principles of extraction from motion photogrammetry. This method works best when the scene stays stable and does not change while the images are being taken. But in real survey conditions, this is not always possible. Temporary objects may enter in the scene and appear in different positions from one image to other. And during the feature matching process, the software may link points located on this moving element, and this can create false matches, add noise to extraction, and introduce geometric errors. For this reason, a modular Python workflow composed of 3 stages is proposed to automate the masking operation. The first, check the quality of the images to find any issue that may create problems during reconstruction. The second module detects and segments unwanted objects. And the final module improves the quality of the mask and export the file. The role of the first module is to check the quality of the image before masking and extraction. And this is a very important step because low quality images can reduce the accuracy of feature extraction and image alignment. To evaluate this aspect, we have created an approach based on 3 parameters. The first one is the evaluation of sharpness, used to detect out of focus image or blurred image. The second one is exposure, used to identify images that are too dark or too bright. And the final one is a resolution, used to verify that image has enough detail for extraction process. These values are combined into a single quality score, which can provide us an overall evaluation for each image of our dataset. The second module is based on the YOLO architecture. YOLO is a real-time deep learning model for object detection. During our experimentation, we have customized the model to improve the detection of specific types of objects that should not be present in the scene. In particular, we have found the minimum confidence level was slightly reduced the critical classes, such as people or moving vehicles, in order to increase the recall value and reduce the number of missed detection. In the second stage of this module, the workflow used SAM2 architecture to create the mask. The bounding box detected by YOLO is used as a guide for SAM2 algorithm, then follows the shape of the object more closely and improves the mask boundaries. This model is not based only on color variation, but it also analyzes shape, edges, texture, and image context to produce a more accurate mask. In this way, the pipeline combines YOLO speed and SAM2 segmentation accuracy in one product. And the final module performs a mask post-processing and export stage. First, all masks detected in the same image are merged into a single occlusion mask. Then 3 operations are applied, and dilatation that expand the mask boundaries by 5 pixels to include some parts that are missed during segmentation. And after that, we make a cleaning stage to remove very small and isolated area, which are identified as likely false detection. And finally, fills internal gaps, so we can produce a solid and continuous mask. After this process, the masks are exported to the format required by different extraction from motion platform in many formats. To evaluate the pipeline, we used 3 datasets with different setup. In the first, we have make and capture in urban area using both a drone and digital camera. The second dataset represents a rural environment captured using only a drone, and the third represents an indoor setting captured using only a digital camera. The urban and rural survey showed a good and consistent image quality, but indoor survey was more challenging because artificial lighting caused blur and loss of detail in the dataset. So some images in this dataset were not included in the next processes because their low quality score. The processing pipeline was applied to the full dataset, enabling the automatic detection and masking of the most objects present in the images. And in this table, we have compared the proposed method with the standard workflow across the 3 datasets we have used. In all cases, the error decreases. This means that the image alignment is more consistent and include fewer incorrect matches. Type point multiplicity also increases slightly, and this value suggesting that the remaining points are visible in more image and are more stable as reconstruction. At the same time, the dense point cloud becomes slightly smaller because temporary object and geometric noise are removed. Overall, the automatic mask produced from our workflow show us a cleaner and more consistent extraction from motion rec extraction. In conclusion, this work showed that computer vision models can be successfully integrated into photogrammetric processing workflow. The results show consistent improvement under different survey conditions, including lower reconstruction errors and cleaner three-dimensional models. However, some challenges remain, particularly in crowded scenes and in the presence of moving vegetation. Future work will focus on temporal information and a more complex environment with some larger test data set and further improvement to the calibration process. Thank you. Thank you for your attention.
Thank you very much, Riccardo. Just a question by my side. You told that you use a pre-trained model, right? Why you didn't use a specific model to train?
We use model pre-trained on the COCO dataset that include about 80 object categories. So we consider it enough for recognize the relevant object that we usually have in photogrammetric survey, including people, cars, bicycle, trucks, and so on. However, specific training or fine-tuning could be useful in future work for recognize some less common object, or for approaching to some more complex scene that are very different from the original training data.
Okay, thank you very much. Any other question from the audience? No, okay. Okay, let's move to the next presentation. It's Michaela Falcone from Polytechnic University of Bari. Michaela, are you online?
I'm here.
Okay, you can hear me, perfect. Okay, when you want, you can share your screen and you can start.
One moment. Okay. It's okay? Can you hear me?
No, we can hear you, but we can't see your screen. Probably could be a question of browser. You shouldn't use, we have some problem with Google.
One moment. I don't know
You
why.
should try another browser.
Don't know why. I don't know, Alberico.
Okay, probably you should try to exit the room and come back in the room again using another browser, no, not Google, I don't know, Edge or something like that. But in the meantime, we can move to the next presentation that should be made by Mr. Yanzu Xu. I don't know if it is online, and sorry for my pronunciation. No, I can't see him.
No, maybe I'm okay.
Now, okay. We can see your screen, of course.
Okay. And now?
Okay, yes. Now
Okay.
we see you.
Thank you. I'm sorry. Okay.
Very much.
Okay. My work today is about the certification in Italy, legal responses among European Union influence, national regulation, and differentiated regionalism. This presentation starts from a simple question. How does the Italian legal system address the certification? The topic is important because the certification is no longer an environmental issue only, but also a problem of governance, territorial inequality, and legal effectiveness. My goal is to show how international and European inputs have been translated into Italian law and to compare the regional responses of Apulia and Sicily. The certification is a useful case study because it sits at the intersection of environmental protection, territorial planning, and administrative capacity. In Italy, the issue is especially relevant in the south, also called Mezzogiorno, where soil degradation is linked to water scarcity, erosion, salinization, and climate change. So the problem is not just whether the law recognizes the certification, but whether it is actually able to address it in a coherent and effective way. In Italy, the certification is also a governance problem. The areas most exposed to it are often the same areas where institutional capacity is weaker, and this means that the legal response is uneven from the start. In other words, the territorial divide is not only ecologic, but also legal and administrative. At international level, the main reference is the 1994 United Nations Convention to combat desertification. At European Union level, however, the legal response has long been indirect. For many years, indeed, the EU addressed the issue through separate rules on soil, water, climate, biodiversity, and agriculture, rather than through a single soil framework. Today, the situation is changing. Recent developments, especially the Soil Monitoring Directive and the Nature Restoration Regulation, point toward a more integrated approach. The soil is increasingly being treated as a legal interest per se. This is a significant shift because it moves the debate from fragmented environmental protection to a more coherent soil policy. In the Italian framework, the situation is still marked by fragmentation. The main strategic reference is the National Action Programme adopted in 1999, which, however, remains mainly a planning instrument rather than a binding legal regime. The Environmental Code is the main normative core, yet it deals with the certification indirectly through provisions on soil, water, and territorial planning. So, Italy does not have a specific and organic law on the certification. Instead, the topic is spread across different sectors and legal tools. This is why the National Plan for Adaptation to Climate Change and the National Recovery and Resilience Plan are important, but not sufficient. They translate the certification into adaptation, resilience, and territorial protection policies, but they do so within a largely programmatic logic. The result is a system that has several instruments, but still lacks a fully unified legal architecture. The financial dimension is also crucial. Many measures against soil degradation are supported by the National Recovery and Resilience Plans and the Common Agricultural Policy for 2023-2027. The 40% allocation is reserved to the Mezzogiorno, and it is especially relevant because it links funding to territorial cohesion. But the key points is that funding can support action, yet it cannot replace a substantively legal framework. As a matter of fact, the quality of implementation still depends on the coordination, monitoring, and administrative capacity. The Italian Mezzogiorno includes the most vulnerable areas, and it also where the implementation is more difficult. This means that the problem is not only the environmental exposure, it concerns also enforcement capacity. Formally, the rules may be the same, but their effects differ widely depending on local institution, planning capacity, and administrative continuity. So the North-South divide is not simply geographical. It is also legal and institutional. This slide shows the North-South asymmetries in terms of share of vulnerable areas. Now let's start with Apulia. There, the desertification problem is addressed mainly through territorial and landscape planning rather than a dedicated regional law. The key instrument is the Regional Territorial Landscape Plan approved in 2015, which connects landscape protection, territorial governance, and a more responsible use of land rather than the desertification specific. In other words, Apulia does not treat desertification as a separate legal category, but as a part of a broader territorial management strategy. It's also worth noting that Apulia has developed a fairly solid base of knowledge. The region has worked on identifying vulnerable areas and on tools linked to draft control, land protection, and desertification prevention. That is a real strength because it allows policy to be more target and evidence-based. However, from a legal standpoint, the framework still lacks a fully autonomous regional discipline specifically devoted to desertification. So the Apulian model is coherent, but it remains mainly planning-oriented rather than normatively self-standing. In Sicily, the picture is different. First of all, Sicily is one of the 5 regions Italian regions with a special statute. This gives the region broader power in files connected to soil degradation and territorial management. On this basis, in 2019, the Basin Authority adopted a regional strategy for combating desertification. This is significant because it gives to desertification the issue greater institutional visibility and makes it more explicit within regional policy. The Sicilian strategy is also supported by mapping, monitoring, and sensitivity indicators, which help to identify the most vulnerable areas and to set priorities for intervention. In addition, projects such as Life Desert Adapt have strengthened the experimental and adaptive dimension of the response, promoting approaches such as agroforestry and regenerative agriculture. So, compared to Puglia, Sicily exhibits a more explicit and structured policy, even if the response remains mainly programmatic rather than fully legislative. The comparison between the 2 regions is revealing. In Apulia, the desertification is absorbed by landscape and territorial planning, while in Sicily it gains stronger institutional visibility through a dedicated strategy. In both cases, however, the legal response is still fragmented. So the 2 regions differ in their institutional style, sharing the same structural limits. They rely on programs and plans more than on binding integrated legal rules. In conclusion, desertification is a key test for environmental law. because it shows the tension between uniform protection and territorial differentiation. It also shows that having many instruments is not enough if the instruments are not coordinated, enforceable, and backed by stable administrative capacity. So the central challenge is not just to recognize the problem, but to build a more coherent system connecting legal standards, monitoring, funding, and territorial implementation. In the end, in Italy, the decertification is a stress test for multi-layered environmental governance. It shows the limits of fragmented action, but also shows the potential of a more integrated approach. The future challenge is to turn planning and funding into effective soil protection and to ensure that the legal system can respond not only in theory, but in practice. Thank you so much.
Thank you, Michaela. Now, the question is, why did you choose Puglia and Sicily? Apulia, I can understand you are from Apulia, so that's why. Why Apulia and Sicily?
Well, I choose Apulia because they are two regions particularly exposed to desertification, but at the same time, they show two different regional models. Apulia is interesting because it addressed the issue mainly through territorial planning, landscape protection, and land governance tools. Sicily, on the other hand, is useful for understanding how spatial autonomy can support a more explicit and structured strategy on the issue. So, comparing these two regions makes it possible to observe two different legal responses to the same phenomenon. Moreover, among the 5 special statute regions, desertification is felt more strongly in the south, especially in the highland and the most vulnerable southern areas. In this framework, Sardinia is a very relevant case because the issue is addressed mainly through environmental, agricultural, and water management policies. However, compared with Sicily, the response is more sectoral than autonomous, since there is no equally explicit and structured regional strategy specifically dedicated to desertification.
Okay, thank you, Michaela. Thank you very much.
Thank you too.
Let's move to the final.
For your patience.
Okay, thank you. Let's move to the final presentation. The work should be presented by Mr. Jansu Xu, if I pronounce it well, more or less. Are you online? No. I see. I can see you. Can you hear me, Janzu? So, no. My microphone is on. Okay. Is. Sì, c'è il. Io non lo posso. Okay, try to write in chat. We can't see your screen and we can't hear you. No. Probably the previous presenter is still sharing her screen. Okay, now. Michaela, are you still sharing your screen?
No.
Okay. We already did. But can you hear us? Probably you should allow the browser to access your microphone and your camera. You can try to restart the computer. You can try to restart your PC. The last attempt, then. I don't know how to help. If you are in the room with another guy, or you can try another PC. Or if you can access another PC. No, Giulio, we can't hear you. You mean my volume? No, non l'ho toccato. No, we can't hear you. We can't hear you. And also, Juno, we can't hear you.
Can you hear me now?
Yes, we can hear you now.
Oh,
Now, please try. Okay. Now you should try to share your screen. The second problem.
okay. Finally, thank you so much. I think it's the connection, Polynesian connection.
Yes, probably was the connection. Can you share your screen now?
Yes. Can you see it?
Oh, perfect. Oh, right. Please, the floor is yours. Thank you very much for your effort.
I will start. Okay. I'm so happy to be here to share our research with you. I'm Jian Xu from Polytechnic of Milano, and our topic is an integration framework of infrastructure heritage building information modeling with historical GIS for reconstructing infrastructure heritage evolution. The case study is the Taiping Link corridor along the Chinese Eastern Railway. On the World Heritage list, there are 4 historical railways. And during the conservation process, the railway heritage has to face some problems. The first one is it's very difficult to document each site, and another one is the management in the sustainable development. Because they have some problems, the first one is the historical railway can be regarded as the linear cultural heritage. It has a large spatial extent and disappeared size distribution. And during the past years, the railway heritage has complex historical transformation in different management periods. And also during the past years, the heritage has accumulated a lot of data and source. It has multiple types and multiple source. So we need the conservation needs cross-scale integration from individual sites to corridor systems. The existing heritage building information modeling, also the HBIM for infrastructure workflows remain insufficient for corridor scale heritage. The object level HBIM focus mainly on individual historical buildings or monuments. And the infrastructure HBIM is effective for assessed level modeling, but for the corridor scale heritage requires HG's historical GIS or GIS integration. And the integration of BIM and GIS still face issues in interoperability, semantic transfer, and georeferencing. The field workflows address the extent vanished and transformed sites within one integrated framework. So in this way, the railway heritage corridors require a framework that can link assess the level reconstruction with corridor scale historical evolution. The case study is the Taiping Link corridor and is built heritage assessed. The Chinese Eastern Railway main line is the most eastern part of the Trans-Siberian Railway system in China. And the railway was designed to connect the Russia-European part and the Far East. There are 5 spiral lines along the main line to support the railway across the mountainous area. And the Taiping Link corridor is located on the eastern section of the main line. And on the left side, there's a map of the Taiping Link corridor. The right line is the permanent line built by Russian, and there's a yellow line was designed to support the construction period. And in the Audit line was built at the beginning of 20th century. In the 1940s, during the South Manchuria Railway, they operated this line. A new double-track line was built by Japanese engineer. So in the past 120 years, the conservation of the historical railway has to face some challenges. In this system, there's not only infrastructure, also including some operation buildings, including railway stations and some water tower. On the right side is the Holy River Bridge, Bridge 1. It's the first stone artery bridge along the corridor. We conducted 2 field survey in the past years. In 2020, the bridge is here, and then it was recorded in 2024 via the drone photogrammetry. And then in 2024, there's a new road construction project that was applied along the corridor, and you can see the landscape around the area was destroyed. And then in 2025, the bridge was demolished. They built a new bridge to replace the historical one. So under this situation, we proposed the integration workflow to focus on the corridor-oriented to protect the HBIM and protect the assets in this workflow. There are 5 steps. The first one is the database development. It includes the archival database, composed historical maps, drawings, photos, and the textual reports. And another one is the geospatial database. It includes the vector and the raster data, satellite imagery, georeferenced maps, and localized size. Based on these 2 databases, we apply the file survey and the documentation through the joint photogrammetry. And then the next steps are point cloud processing and the multi-level built heritage size reconstruction. We separated the size in 2 levels. One is assessed level, another one is a system level. And in the 4th step is the modeling workflow and accuracy assessment. We applied forward modeling and reverse modeling for different sizes. And the last step is the integration and the remote exercise. We integration all data in a historical GIS environment and the publication the outputs on WebGIS. During the database development, we have to face some problems. The challenging one is how to link multiple evidence because it's a historical assessment, so it has accumulated multiple types of the evidence, including archives, special features, models, and WebGIS outputs. So we developed a unified 12-character heritage ID system. In this ID, it includes 6 parts: the section of the bridge, the heritage, and their type, and who designed, and their male age. Also, their serial number in the same section, and their current condition. So on the right side is all the infrastructure heritage sites. Each of them has a unique 12-character ID. So it's easy for we to organize multiple types of the evidence. So another challenge is how to reconstruct the corridors through the georeference. We have multiple historical maps, but on this map is the layout of the corridor, but we don't know the contour elevation values of the on this map. So we try to find other evidence in the same album of the Chinese Eastern Railway. On the left side, there are other 2 maps related to the same loop line, the Ping'an loop line. And the first one is a southern-based plan with the contour elevation values. And the below one is the west-based plan with contour lines, but without elevation levels. We can confirm they are the same. They are in the same scales. So we predict and we regard that the historical map along the tightening corridor, they use the same contour scale. And then you can see after the georeference that we reconstructed the corridor, their direction, their layout, and each assessed where they are on the map. And then we reconstructed the history about the evolution about the corridor from the 1897 until 2015, because after 2015, the section was closed and they built a new line to replace this place. So, and then the next step is the field survey and cloud processing. Field surveys were conducted in 2021 and 2024. And we used the Dajiang Air to collect the data. And then these point clouds were generated through the SFM and MVS processing. Point clouds were processed for slicing, filtering, recovering, and HB modeling. And the next one is the selection of the infrastructure HB modeling strategies. We applied 3 different methods for the modeling, because the selection of the strategies according to the evidence conditions. The forward modeling used for the vanished or the poorly preserved sites with strong archival evidence. And the reverse modeling used for the extent sites with sufficient point cloud data. And the hybrid modeling used for the transformed sites with both historical and current evidence. At the assessed level models, they were developed at a level of development 300, while the railway element models are developed at the LOD 200. So the last step is the integration of infrastructure HBeam and HGIs. The HGs is used as the central environment for multi-source integration. The IFC4 models are imported into the ArcGIS Pro as the 3D feature layers from the Revit and the Civil 3D. And semantic information is transferred into GIS attribute labels. You can find it in the figure 1. And the SRSPK models and the point cloud drive the data science support efficient 3D visualization. And you can find them in both figures. And the WebGIS enables remote access, interactive exploration, and information query. So when the stakeholders, when they review the link, they can find more details related to each site and to see the how the terrain and in this mountainous area will via the WebGIS. So the last part is in conclusion. The framework supports corridor scale reconstruction and documentation. It integrates archival, spatial, point cloud, and model-based data within one workflow. And it links assessed level infrastructure HBeam with corridor level historical GIS representation. And it supports reconstruction of extant, vanished, and transformed infrastructure heritage. Also, we have some limitations in this study. It includes uneven archival data, lack of GCPIs, accessibility constraints, and reliance on the commercial platforms. The future work will extend the framework to more corridor sections and explore XR-based visualization. So thanks for your attention.
Thank you very much. Thank you very much. Okay, we have still some problems. In your opinion, do you think these workflows can be applied to other similar infrastructure? Are there problems with the scalability of this solution, in your opinion?
Could you please? Sorry. Clear.
Can you hear me or?
Yeah, I can hear you.
Okay. Did you hear my question? Okay, thank you very much. We are very late, so we reached the end of this session with some difficulties. So anyway,
Thank you so much. Thanks for all your support.
Okay, no, it's not your fault. It was not your fault. Let me thank all the attendants to this session, all the participants. Let me thank again the University of Minho, and let me thank, of course, Giulio for our technical assistant for his help. And thank you again. I hope to see you next year in the same session at ICCSA. Thank you very much again.
Bye. Thank you.
Thank you so much.
Thank you.